In the previous lecture, we have seen what do you mean by a microarchitecture, what are the different processor state elements used for designing microarchitectures, and what are the different microarchitectures used for designing ARM processor, right? So here we will be dealing all those different types of microarchitectures in detail. First, we are going to see what is meant by single cycle processor microarchitecture, single cycle microarchitecture. So for constructing a single cycle microarchitecture, we will be starting with the construction of a data path. So data path is nothing but it is a path used for connecting the state elements with the combination logic that can execute various instructions. So you have already seen that you will be having different processor state elements and combination logic will be there. For interconnecting these state elements and combination logic, you will be using data path. Then there are certain control signals which will determine which specific instruction will be sent through the data path, right? So in the next step is to construct a control unit which contains combination logic that generates the appropriate control signals based on the current instruction. So first you are designing a data path used for connecting the state elements and combination logic. So next step is you are going to design the combination logic itself. So that is known as a control unit which is used for controlling which instruction should be sent through the data path or which instruction should be executed in the data path using the data path. So you are going to design a data path and a control unit. So as a first step, you are going to design the data path for a single cycle processor microarchitecture. So for designing the data path, the first step is to read the instruction from the instruction memory. So whatever instruction you are stored in the instruction memory, you should read the first instruction. So how will you point to the first instruction? Using the program counter. We have already explained. So in program counter, PC dash means it is the next instruction. PC will be giving the current instruction. Address of the current instruction. PC dash will be address of the next instruction. PC will be holding the address of current instruction. That address will be given to the A port of instruction memory. So what will happen? Whatever instruction is present in that address will be sent out through the RD port or in the instruction port, right? So by using these two connections, you are reading the first instruction from instruction memory, you are sending it out through the instruction bus. Then in the second step, you are going to make the connection between the register file and the instruction memory. That is the second step. So before going to deal with the register file, you need to understand that we are going to design the microarchitecture for only three main types of instruction. First one is data processing instruction, load store instruction, and branch instruction. We have already told. So in the next step, we are going to design the data path for load instruction, right? So the first step of designing data path is reading the instruction. So the reading the instruction remains the same for all the different types of instructions. First you need to read the instruction. So that step remains the same. From the next step onwards, you are going to concentrate on different types of instructions. So first you are going to design for load instruction. So before designing the data path for load instruction, you should understand what do you mean by binary encoding or instruction encoding for load or store. So what do you mean by binary encoding or instruction encoding? If you are writing an instruction in ARM, say LDR, something you are writing an instruction, add R1, R0, R2. If you are writing an instruction like this, the processor cannot understand this instruction. Processor can understand only some binary numbers. So what you should do, you should convert this instruction into a code known as operation code. which will be containing, in the case of in the case of ARM, it will be containing 32-bit binary numbers. Whatever instruction you are writing, it will be converted into a 32-bit opcode, right? How the instruction is getting converted from the actual instruction to the opcode is explained by using the binary encoding or instruction encoding of that particular instruction. So for the LDR or STR instruction, binary encoding will be done like this, right? So whatever instruction you are writing, it should be converted into a 32-bit opcode in ARM. How or how this conversion is done for each instruction is explained by binary encoding technique, right? So this is a binary encoding for LDR. So I told you will be having 32-bit instruction. So for all the instruction you'll be having 32-bit binary encoded opcode. So for LDR or STR, from the bits from 0 to 11, these 12 bits are used for representing the offset address, right? So for load, what do you mean by load? You are going to load the instruction from a particular memory location to registers. Loading means you are loading from memory to register. So for reading something in a memory, you should specify the address, right? And for load and store, you will be having, always you will be having a base address and an offset address. So first you will be giving a base address. From that base address, you will be adding some offset for getting the next address. Say if you want to add 5 numbers, what you will do? You will be using a base address and you will be giving it to a pointer, and the pointer will be incremented to the next location. So that incrementing to the next location is known as the offset, and the base address remains the same. So if you are adding the first offset with the base address, you will get the actual resultant address. If you are adding the next offset to the base address, you will get the second resultant address. So for load and store, you will be having a base address. Base address will be again 32-bit address. Offset will be, in this case, offset will be 12-bit offset, right? So here bit number 16 to 19 is used for storing the base address, right? Or it is used for storing the base address register, because here the base address will be held in a register known as base register. So I told you are having registers from R0 to R15. So in which register you are storing the base address, that is specified by Rn. So 4 bits are there: 16, 17, 18, 19. Using these 4 bits, you can configure any one of the 16 registers. Right. So if you are storing the base address in say R1, what will be this value? 0001. So 0001 represent register 1, R1. That means if you are writing here 0001, you can identify that you are going to store the base address in a base register known as R1. Right. Similarly, offset 12-bit offset will be given directly here. Whatever immediate value, 12-bit immediate value you want to give, you will be giving it here, right? Then, so by adding the base address and the offset, you will be getting the resultant address, and from that resultant address, that is the address of the memory actually. From that memory, you will be reading the data, right? And that data should be loaded into a destination register. That is what I told. You are reading from memory to a register. So that register is known as a destination register. So destination register is configured by these 4 bits: 12, 13, 14, 15. So by configuring these 4 bits, you can configure the destination register, right? In the case of LDR. In the case of STR, it will be the source register. In STR, what you will do? You will be loading from a register to the memory. So this forms the source register, and the memory address will be calculated by adding base address and immediate. So in the case of LDR, RD will be the destination register. In the case of STR, RD will be the source register, right? So in our case of microarchitecture design, we are not concerned about the shift, because actually in LDR and STR, you can incorporate some shift operation also, but for time being you are not considering this shift operation now. You are considering only this, right? So here you need to know only these few things. No need of considering all these things. You need to consider, you need to understand that you are having a base address, you are having an offset address. When you are adding these two, you will get the resultant address. So from the resultant address of the data memory, you will be reading the data from that address, and that data should be stored onto this destination register. So destination register is specified by 4-bit value. Similarly, base register is also also configured by the 4-bit value. And for each instruction, you will be having a conditional execution field, that is a 4-bit field. For each instruction, 4-bit field will be there, conditional execution instruction, that we will see when you are dealing with the conditional execution. Then the next 2 bits will be known as the opcode field, right? So this opcode field 01 stands for load or store, right? So in the, this is a 2-bit opcode field. In opcode field 01 stands for the load or store instruction. Conditional instruction, conditional execution, there are 4 bits are there. There are 16 conditions possible. All those things we will see later. So now we are concentrating on base address stored in base register, immediate value of offset stored in the instruction itself, and the destination register configured here, right? So this is known as the binary encoding for the store or load. So for designing the data path, the first step you have already seen. You are connecting program counter to the instruction memory so that the current instruction can be read from the instruction memory and given out to the RD port. In the next step, you are going to connect this to the register file, right? For that, here you are going to use in the first example, you are going to use LDR instruction, right? So for understanding the LDR binary encoding, we have seen this. So in this step, what you are going to do, you are going to connect the instruction bus to the register file, right? So in the register, so the next step is to read the source register containing the base address, right? So first I have loaded the instruction to the RD port. Next, since it is an LDR instruction, in the next step you are going to read the base address, right? I told you, you need to read base address and immediate value. So since it is a LDR instruction, first you need to read the base address. Where is this base address stored? In the source register. Which is the source register here? RN. So RN is used for storing the source register, so storing the base address. So you need to read from RN. So what you will do, which is used for configuring RN, which bits? 16 to 19. So 16 to 19 bits of instruction, that is binary decoded instruction, will be connected to A1 of register file, right? That is, these 4 bits of the instruction are connected to address input of register file, that is A1. So what will happen? This 4 bits will be configuring, or it is used for configuring the base address register holding the base address value. So 16 to 19, these bits are given to A1 address port of register file. So what will happen? Whatever instruction is, or whatever data is present in this address of the data memory will be sent out. So what will be stored in this address, or what will be stored in this register address? Say A1 is used for configuring or reading or writing from a particular register. It should get a 4-bit value. So here if I am using base address register as R1, you should give this, you will be getting this bit as 0001, right? So by giving 0001 to A1, you are configuring, or you are selecting R1. Then from that R1, what is stored in that R1? The base address. So the base address stored in the R1 will be available in RD1, right? That is how it is happening. So by using these two steps, you are reading the instruction from the current program counter value, and in my case, my instruction is LDR. So since it is LDR, the next operation is to read the base address. So for reading the base address is stored in a register known as source register or RN, right? So what you should do, by using the register file, you need to read the content of RN, right? So how will you configure RN? By using these 4 bits connected to A1. So by using 4 bits of A1, you can read the RN or you can configure RN. In my case, let us take RN is R1. So you should give 0001 to this. That will be already available in the instruction 16 to 19. So first base address stored in R1 will be available here, right? So that is how you are selecting a particular register. In this case it is Rn, and you are reading the value stored in Rn. The value stored in Rn is nothing but the base address. So now by connecting 16 to 19 bit of instruction to A1 of register file, you will get the base address in RD1, right? So I told the base address will be stored in say R1. So base address will be available in RD1. So you will get the base address here. In the next step, so I got the base address. In the next step, you need to get the 12-bit immediate value, right? So now I got the base address in RD1. Next step, I should get the 12-bit immediate value, right? And the 12-bit immediate value is stored in instruction bits from 0 to 11, right? So the offset value is stored in the immediate field of the instruction that I have shown here, 0 to 11. So these are the 12-bit offset. So you need to read that, then you need to perform something known as 0 extending to 32 bits, because you are going to add with the 32-bit base address, you are going to add the 12-bit immediate value to the 32-bit base address. So you are going to extend this 12-bit value to 32 bits, right? So remaining bits you need to add. So for 0 extend, what do you mean by 0 extension? You will be having 12 bits, that is IM, a external IMM. So first 0 to 11 bits will be the offset, that is the 12 bits. Remaining bits from 12 to 31 will be 0. That means from bit number 12 to 31 you will be putting zeros. So for performing the 32 bit the 0 extension, you are using this block. So when you are giving 0 to 11, that is 12 bit offset here, at the output you will be getting the 12 bit value, and from bit number 12 to 31 you will be having 0. You will be getting 0 extended offset here, right? So in the previous step in RD1 you got the base address, and here you are getting 32 bit offset. So in the next step what you are going to do, you need to add this base address and offset. Since you are using LDR instruction, first you need to get base address, then you should get offset, then you need to perform the addition of these two. So for adding these two, you are using the same ALU. So in the next step, you are going to connect the ALU, right? So here you can see you are going to connect the ALU. In the ALU, the first operand will be the base address, that is known as source A. Second operand will be the 32-bit sign extended immediate value. These two, base address and the immediate value, should be added and should be given as ALU result. So for performing some operation in the ALU, you are having an ALU control signal. It is a 2-bit control signal. If you are giving it as 0 0, ALU will perform the addition, right? So ALU is controlled by ALU control signal 2-bit value. If you are giving 0 0, the base address and the immediate value will be added together and will be given as ALU result. What are the other control signals for ALU? If you are giving it as 0 0, it will be add 0 1 or etc, etc, right? So in the first step, you have read the first instruction by using PC and instruction memory. Then from that decoded instruction, bit number 16 to 19 is used for decoding the base address. So here you are configuring the base address, then base address value will be available here. In the same instruction, bit number 0 to 11 is used for specifying the offset. Then sign extension is used for creating 32-bit value. Then in the next step, ALU is added to add base address and the offset. Right, so you got the destination address here. So for performing the addition operation, you are giving ALU control signal as 00. So now here you got the final address. Next step is you need to read the content of data memory with this address. So in the data memory, you will be having a location with this address. From that address, you need to read the data. Right. So in the next step, you are going to connect the data memory. Right. So in the next step, you are connecting the data memory. So in data memory, how it is working? Whatever address you are giving here, the content of that data memory location will be given out through this RD. Right. Load means you are going to read the content of data memory to a register. Right. So for generating the address location for which data has to be read from data memory, you are doing all these things for generating the address, and that resultant address you are giving to a port of data memory. So what will happen? From the data stored in this, corresponding address which is given here will be read out through this. Say if the address is 000001, whatever data is stored in that 00001, that content will be sent out or read out through this RD. Right. So what will happen? Then what you should do? That read data should be written to the particular register. So here in this block, you are reading the data from the data memory specified by an address. So that data will be coming out, and for the load operation to complete, what will happen? You need to read the data from data memory. You should store it in a destination register. Right. What is the destination register? It is nothing but your RD. Right. So RD is specifying the destination register to store the content of data memory. So RD is specified by bit number 12 to 15. You should keep in mind. So 12 to 15 is used for representing or configuring RD. So in this step, you can see that the 12 to 15, that bits are connected to A3 of register file. What is the use of A3 of register file? A3 port is used for configuring the register file for the write operation. So RD, so what I told in LDR, you are reading from data memory, you are writing to a destination register. Right. How will you configure the destination register? It should be configured using A3, 4 bits of A3. That is bit number 12 to 15 is used for configuring destination register RD. Right. So by using this 4 bit, what you are giving to A3, you can configure the register for write operation. If you are using A1 and A2, you are configuring the register for read operation, right? So two read ports are there in the register file. One write port is there in the same register file. So here you are going to read the data memory. You are going to write it into a destination register. So how will you configure the destination register for write? By using these 4 bits. So these 4 bits should be connected to A3. So by connecting these bit number 12 to 15 to A3, you are configuring the destination register for write operation. And what data you need to write? That data should be given in W3. Whatever data you need to write, that data should be given here, and to which register you need to write, you are configuring by this. So whatever data you want to write is available in this line. So this line you are connecting to W3, and to which register you need to write is configured by using this line connected to A3. Finally, you need to perform the write enable. You need to make write enable as 1. So you need to make WE3 as 1. So you are using a control signal known as register write. This register write should be 1. So write enable will be 1. And finally, after giving the write enable, you should give a clock. So at the rising edge of the clock, provided write enable is 1, So in the rising edge of the clock, provided write enable is 1, whatever data is connected to W3, that data will be written to the register configured by A3. So here I am configuring A3 as destination register by using bit number 12 to 15. So to that register, whatever data you are giving will be written, right? That is what is done in this operation, right? So you are reading the instruction here. From that you are getting the, you are configuring the base address register, so you will get the base address value here. Then you are getting the 32-bit offset here by using an extension block. Offset and base address you are adding here by using the control signal 00. So you will get the actual destination, you will get the actual address from where you need to read the data value. That address you are giving to a data memory, right? So whatever data is present in that address will be sent out through RD. That content you are writing back to a register file known as RD file, that is configured by using these 4 bits, right? So data you have given here, register you have given here, and for performing the write enable should be made as 1. Finally, when you are giving the clock, in the rising edge of the clock, the data what you have given here will be returned to the destination register. That is how you are performing the load operation. In the next step, you want to increment the program counter to the next location, right? So first you have read the current instruction. In the next step, you need to increment to the next location. So how will you increment the program counter to the next location? You need to add +4 to the program counter, because here you are having a 32, ARM is a 32-bit processor, so you are using byte addressing. So the location +4 will be pointing to a next word, right? Other, if you are giving +1, that means to the next byte only it will be incrementing. Since it is a 32-bit register, you need to add +4, right? So for incrementing the program counter, you are adding one more ALU here with the plus operation, and one input is 4, right? So by using this, program counter +4 will be done, and the new program counter will be given as input to program counter, right? So this is how you are incrementing the program counter to the next instruction, right? So this is how you are incrementing the program counter to the next instruction. So this completes the store operation, load operation. Then in addition to that, I have told there is one more option in the register file. That means you can read R15. If you are reading R15 in the file register, you will get actually program counter plus 8. So program counter +4 you will be getting here, right? Then program counter +8 if you want to get, you are adding one more ALU block here. So program counter +4 +4. So you will be getting program counter +8. So by using this ALU or adder, it is nothing but an adder, you can, if you are reading R15, you will be getting program counter +8. And so in order to get this program counter +8, you are adding one block, and one more additional multiplexer you are adding here, and the control signal is PC source. If the PC source is 0, what will happen? The program counter +4 will be given as input to the program counter block. If you are giving 1 as a PC source, the output of read data will be given as input to the program counter, right? So by using the load instruction, you can read the data, right? And that data can be also fed into the program counter. So by using this ALU, it can be used for generating the data as well as address to the next instruction, right? So you can use the LDR instruction for reading the data as well as generating an address for next instruction. So that is what is told here. Reading the register R15 will be returning PC8, right? So therefore another adder is needed to increment the PC and pass the sum to R15. Similarly, R15 will be updating the PC. Therefore, PC dash may come from the result of the instruction. So you can have the PC dash generated from the result of LDR, right? So PC dash can have two sources. One source you have already seen. PC dash will be PC plus 4. That is one source. That means you are incrementing the program counter by 4, or you can increment the program counter based on the address which is generated here, right? So in this case, the data memory will be storing the address, right? So as a result of this operation, you will be getting a resultant address. That address can also be fed into the program counter. So you can calculate the address and give it to the program counter, or as it is, you can increment the program counter by 4 and you can give it to the program counter. So by using PC source, you are selecting whether the address you are generated from the operation has to be fed to the PC, or plus 4 has to be fed to the PC. So this is how LDR operation is working.